Well, I am continuing from the previous class in which I just wrote about the nickel arsenic structure. So I think we had the last slide that talked about the nickel arsenic as some kind of prism there. The prism I drew was something like this. Okay, and then if you connect these points, you get a prism, and this is what you have. Okay, so all these points at the end will be represented by the blue as nickel. 1, 2, 3, 4, 5, 6. And in between you will be having some large space, large gap. This gap, if you imagine this in a three-dimensional direction, in this particular gap you can have the central atom as the arsenic, and this one as the nickel. So these are the nickel atoms, are those things that you see here in this particular portion. Okay, if you make a triangle like this, the top portion of the triangle like this, it is going like this. Okay, this triangle is what I have drawn here. If you number this as 1 and this as 2 and this as 3, I am going to write this as number 1, 2 and 3. Okay. Now below this 3, you see a ball, another blue ball hidden there, and another blue ball hidden there, another blue ball hidden there. That means if you see from this particular position, if you have eye here, this ball is completely hiding this particular ball. This is in the middle. Arsenic is in the middle, but exactly above this is this one. Likewise about this 2, this one is there. Likewise about this is one. So if you see from above, all this ball will hide this ball, or this ball will eclipse this ball, and this ball will eclipse this particular ball. Okay, that is the arrangement, and the first layer happens to be this one. Okay, the first layer, and the second layer, if you see it from the top, the second layer will be this one, and then the third layer will be this one. Okay, you can see that the first layer is nickel, second layer is arsenic, third layer is again nickel. So you have NiAs, 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 right? If you consider this as layer A, this as B, and this as A, and this as B, and this as A, you call as layer AB type of arrangement. Okay, so if you include some other thing, now the arrangement may be changed. You can have a third atom in between, and you can call it as a ABC, like that. The three layers will not be on top of each other. Now you can write A is parallel with another A. This is parallel to this one. B is parallel with another B. So likewise you are going to define the nickel arsenic structure prism, and this is dependent on the type of atoms that are there, whether they are larger or smaller. They occupy different things. Now one good fallout of this is, if you can see that if you have a triangle like this, three atoms like this, we exactly drew another triangle like this, but there is other way around. If the next layer itself is, if you see from there, if the next layer itself goes like this, okay, it is not at all a prism, and you can have the central metal atom like this, and this may be surrounded by 6 atoms there. 1, 2, 3, 4. This one is 5, and this one is 6. 1, 2, 3, 4, 5, and 6. I'm going to add these lines, and then you can see that when I add these lines, and I can connect it in this way, and I'm getting something like an octahedron. If you have two parallel layers like the same atom, you get a prism. But if you have one layer like this, another layer quite opposite of like this, you get an octahedron. Look at the geometrical change that is there. And for that, it is mentioned in this slide that you have this elevation. Elevation means how much it is raised and how much it is clear. Half means it is raised half, and then 1/4, and then 3/4. So that is, if you have this elevation means, how, if you see this plane of the paper, how far it goes. Okay, so let me take this, if I can draw the lines here like this. Okay, now this triangle is quite opposite of this one and it resembles this one. So therefore I can say that nickel atom, this nickel atom is in a manner similar to this. Therefore, nickel atom is surrounded by arsenic atoms in an octahedral pattern. Octahedral pattern. That is what it is. There are some elements like gallium arsenide or some other elements in which you cannot have the arrangement like this. This and this may be a kind of similar arrangements, and therefore you can have a pattern which is close to prism. Okay, one good way how you can understand the octahedral pattern is, if I draw the octahedral, it will be having a face like this. You can see that you are having uh, four faces here, 1, 2, 3 and 4. Four faces on top and four faces at the bottom. So they give right to 8. That is why you have this octahedral. Okay, this arrangement, which we can put it like this as a star type. This is exactly this arrangement. It constitutes a kind of octahedral type of arrangements. So you can rotate this back. You can push this. This is the top layer. Top layer I am just double writing. If you rotate the top layer like this, it goes here and this goes here. Then you can have a layer like this and again a layer like this. Okay. So this layer comes to, after rotation, to about 360 by 3 is 120 degrees. You get back this particular layer and another layer is this. So this will be in a sense will be eclipsed type of layers, and that is meant to say here. Uh, that is what is being written here. In the writing part, you are supposed to write how much these atoms are there. Here, it is mentioned in this particular slide that the 1 by 4 and 1 by 2 or 3 by 4 is uh, the direction perpendicular to the screen. Perpendicular to the screen, if you have just parallel to the screen, it is 0. Just above that you can have 1/4. Above that you have 1/2, and above that you can have 3/4. So he is trying to explain in terms of the elevation from the paper, and again you can just write that it comes to about octahedral. If you have the arrangement for the octahedral arrangement, then the elevation of the atoms take up this. Okay, they take up the trigonal prism and not an octahedron, right? Here is an octahedron is only when nickel is at the center and arsenic is around there. There is another way in which you can say arsenic at the center, and then you are surrounded by the nickel atoms around. Okay, if you have arsenic at the center, you can see that here arsenic is at the center, and the nickel atoms are occupying a particular pattern. You see both this, they appear like this one. See, this is the nickel atom. 1 nickel, 2 nickel, 3 nickel. You get a triangle like this. Okay, and then again, if you have arsenic at the center, you get another triangle which is eclipsed. Therefore, you get a prism pattern like that. Okay, if that is rotated, in the case of nickel at the center, you can write that nickel is surrounded by arsenic in an octahedral pattern, whereas arsenic is surrounded by nickel in a trigonal biprism pattern. That is what is being written there. Okay. In the Na structure, the Na atoms do not form ABAB or HCPRR of close packture. In fact, the layers of nickel atoms are directly on top of each other. In contrast, for the nickel, the locations of Na plus and Cl minus are interchangeable. Okay. And this is a quantitative type study, that you cannot change. It is already there. This is a study of the crystal. You just have to increase your knowledge about the type of crystal, and you cannot force nickel to occupy the structure in the HCP type or any other sodium chloride to occupy any face centered and body centered giving. Okay, we're not going to this. You can stop with this explanation. Now let us move to the next part of the slide where I'm going to explain more about this nickel arsenic structure in another pattern. There, this is another diagram in which nickel is taken as an unshaded proton. So this will be the nickel. Okay, you can see that nickel is connected by another nickel, another nickel, another nickel. There, arsenic is at the center, and here you have nickel, nickel, and nickel. This again occupies another triangle. So these two triangles are almost over each other, and you can call them as the eclipsed. So therefore, if eclipsed means these happen to be trigonal biprism. So let us look to what is happening to the nickel. So let us take, I am taking this as nickel here. Okay, nickel is surrounded by one arsenic here, another arsenic here, and another arsenic there. Okay, if you draw a triangle like this, you can also get a triangle. You can also get a triangle like this. Okay, in this triangle, you can see that this side and this side are quite opposite. Opposite means one you draw like this, the other one you draw like this. Okay, this one is this one, and this one is this one. Okay, the same. Now there is another structure of the same pattern which you call it as the gallium arsenide, which is quite close to the SCP form. In the SCP you have hexagonal close packed structure. Hexagonal close packed structure that is taken up. This is the hexagon that is there, that is mentioned there. 2, 3, 4, 5, 6. Then you have another one in the center. Again, you can take up the internal structures there. You can see that this triangle and this triangle are quite opposite. Okay, we are not getting like this. We are getting like this. This one is true, and this one is not there. Okay, that arrangement is giving rise to some kind of internal pattern. Again, you can see that this is a cube. In the cubes, you have internal space so much. The space is large. The molecules can be occupying there. So this is a kind of tetrahedral arrangement there. You can see that this is at the center. You are having 1, 2, 3, and 4. These 4 atoms, occupy the corners of a cube. Okay, this is the structure. If we say that this is the structure of gallium arsenide, then it exists like that only in hexagonal close pattern, and it's a qualitative study method. Okay, here is another structure, titanium oxide. So this gives rise to your more understanding of that. Now all this this is one octahedron there, 1, 2, 3, 4, 5. Another one at the back. It should be connecting like this, and we will have 6 structures. If you have 6 carbon atoms, it forms an octahedron because this is one phase, and this is another phase, and this is the. If you can see, the third phase is here, fourth phase is on the other side. Okay. Likewise, this is the same thing for this. This is one phase, this is another phase, and then you have another phase here, and then you have another phase like this here. So that is octahedral phase. Okay, the 2 dotted lines, they represent other 2 different phases. So here is this octahedral arrangement is actually inside a cube. Inside a cube, you can see that this is a cube. You see this cube, and you see these atoms there. This one, and this one. You remove this one. The back, it comes this and this one. Okay, so you can have the barium BaTiO3 structure like this, in which the TiO is occupying this type of octahedral structure, but if you include barium, they occupy the corners of a cube. So if someone says that a octahedral arrangement inside a cube it is possible, and this is kind of a regular arrangements which gives rise to several crystalline properties, and they are very interesting also because the empty spaces are not left as it is, and there is a reason why you have most of the minerals that exist on the earth. They do not exist like, for example, they do not exist like alone titanium or alone barium or even alone silicon. So they have something like SiO3 or Mg2SiO3, Mg2SiO4, something like that. They are all those we call them as ores. They exist only in this crystalline form. That is why it becomes very essential for you to understand the crystalline nature of every ore that is there. And here is a question that forms a very basic thing of the crystallography. Also, you need to remember this, even though it may not be asked for you. But it is important that you remember the radius ratio. This is about radiation. How many chloride atoms surround a sodium atom? What is the geometric description of the coordinate system? The ionic radius of Na plus is 97 and Cl minus is 181 picometer respectively. What is the cation to anion radius ratio of the structure? In view of this ratio, do the neighboring chloride ions touch each other? So you should read the question again. So it is never to confuse you. The only thing is, we always have no idea of what is being asked. For that, we have to read the question again. So it says that the radius ratio that is given directly is 97 by 181. So you can see that if it is 0.536, the cuboid form is more favorable, and the ratio is 0.4. We sometimes call it as the packing factor also, and that is dependent on the radius ratio that is there. If the radius ratio changes, you get body centered cube, and if it increases, you get face centered cube or simple cubic. Okay, here in this case of sodium chloride, you get 97/110, which is equal to 0.536. The cation speed octahedral, precisely the radius would be 0.406. Third, the chloride ions do not touch each other. Okay, that is what is being based. If you get something like this 0.414, you can say that it is being touching like that. But here we got a lot of space there. Redox ratio of 0.536, like a great ratio. Okay, therefore they do not touch. That is a simple thing. Whether they touch or not, practically speaking, they don't touch each other because they are held together by ionic bonds only. Okay, so likewise we have something like zinc sulfide and fluoride structures also. This is a kind of structure that forms the basic for several other ores. Okay, here also you can see that in the zinc blend structure you have uh, zinc atom at the center. And if you have four, you must look into where these four atoms are belonging. They are occupying very good space there. Okay, zinc sulfide, they are occupying the corners. Okay, you can see 1, 2, 3, 4. They are at the corners, and this one is at the face center. Face center. Again, this 1, 2, 3, and 4 are corners. This one is the center. So this one is one face. This is another face. This is another face. This is another face, and this is another face. So you have 6 faces of a cube occupied by sulfide, and the inter interstitial means that is between that exists between the ions, that which exists between the ions is occupied by the zinc. Okay, so the classification of the structure usually gives an insight into how these are arranged. Here is another rutile, very famous structure Ta-2. You can see that again. This is quite clear, similar to uh, a very often asked question, quite similar to zinc blend. Okay, zinc blend structure and rutile Ta-2 same, almost the same. But what is the major difference there? You had one more center there, one more atom at this center. Okay, you had only 4. This side you had one more, and this one. Okay, that goes in the back. You had another. So you had 1, 2, 3, 4, 5, 6 atoms in zinc sulfide. But why is that missing? This is missing because in the titanium is larger in size. Titanium is larger in size compared with the zinc, larger in size compared to zinc. Okay, so you can yourselves make how this rhenium oxide is having this structure, and these are all oxygen atoms there at the center. They are at the edges there, and no center portions are empty there. Because of some size of the rhenium ion, they are not occupying the center. Okay. So the arrangements simply vary between. So this is another structure like calcium titanium oxide. So calcium, the cavity which we have empty here is not empty here. It is occupied by some calcium. Okay, every structure gives rise to some interchanging patterns, tetrahedral pattern. So here is another structure of TiBaCO3, another stoichiometric compound, how they are arranged and how these are predicted by the X-ray crystallographic studies. The X-ray crystallographic studies, they actually see the electron cloud. These are all electron clouds, and where there is no clouds, we just they analyze it, and we have to simply connect. So this is a real X-ray technique of finding out the structure of a particular crystal. Okay, so I think it is now clear in how you are writing. This is just an element of another TiO2 structure, uh, polyhedral in nature, and this is a drawing that differs in the ball and stick model and this model. So you don't have to confuse it. And then what it is giving is the X-rays are finding out the electron density by means of the black spots. Okay, there are some 80 techniques, with regard to X-ray identification. Okay, some books even have 300 techniques, like for example XPES, X-ray photoelectron spectroscopy, and XRD, or even simply X-ray scattering techniques, something like that. So several instruments are there that form the nature of finding out the structures and analyzing them. And after you grow them in the lab, the best part is you analyze them and write the structure. And some students, even because these are all inorganic, they use cyclic voltammetry to find out the homonomial gap and use. Okay, so in this video we have just found how the uh, trigonal prisms can be converted into octahedral, how they can be accommodated into the cube, and then the cubic structure relationship with the octahedral structure, and therefore the hexagonal close pattern. Thank you for joining me. See you around soon.